an average of just 36 million miles from the Sun, Mercury is continuously blasted by solar radiation. Surface temperatures here reach a punishing 800 degrees Fahrenheit, creating the ultimate hostile environment. Because of its size and its cratered, barren appearance, the historical baseline assumption for decades was that Mercury was a geologically dead rock, much like Earth's moon, locked in a static orbit. That assumption survived for so long because Mercury is incredibly difficult to observe. The blinding glare of the Sun overpowers Earth-based telescopes, keeping the planet obscured in a wash of light and leaving scientific models entirely unchallenged. It wasn't until NASA's Mariner 10 and Messenger space probes physically traveled into that glare to map the surface that we received high-resolution data. These observations revealed a landscape and internal chemistry that existing models could not explain. Mercury exists as a world of physical paradoxes that challenge the established laws of planetary science. The first problem researchers faced was reconciling a world assumed to be geologically inert with a surface that is still actively changing its shape. This satellite image reveals a massive feature known as a lobate scarp, cutting diagonally across Mercury's cratered surface. Notice the 100-kilometer scale at the bottom. These are enormous thrust faults, some towering over 1.5 kilometers high. This topographic map uses color and white arrows to highlight specific regions where the solid crust has been vertically displaced. These deformations are caused by Mercury's interior anatomy. The planet possesses an unusually massive iron core that makes up 85% of its entire radius, and that immense core is slowly losing heat. As the core cools, the planet's total volume decreases. The solid silicate crust is forced to compress, buckle, and overlap itself. Recent scans along these overlapping scarps show fresh tension fractures, known as grabens, splitting the ridges. Because these microscopic fractures have not yet been erased by meteor impacts, they are incredibly young. Their presence proves that Mercury's core is still losing heat today, meaning the entire planet is actively shrinking and destroying its own surface in real time. The second paradox contradicts the mechanics of planetary cooling entirely. A planet supposedly too small to maintain its internal heat still possesses an active magnetic shield. Based on its minuscule size, Mercury should have radiated all of its internal heat into space and completely frozen its core solid eons ago. Yet, as spacecraft passed the planet, their magnetometers registered a persistent global magnetic field actively surrounding Mercury. Generating a magnetic field absolutely requires a dynamo effect. The core of the planet cannot be solid rock. It must be at least partially molten, spinning and constantly convecting to create electrical currents. This unexpectedly weak but active shield constantly battles the intense solar wind. The interaction is violent. The magnetic field folds into aggressive magnetic tornadoes, funneling plasma down to the surface and blasting atoms high into the sky. Finding an active internal dynamo inside a planet of this size forces astrophysicists to reassess our models of how planetary cores cool and maintain heat in the inner solar system. The third and most extreme paradox involves surface chemistry. We have found frozen water on a world hot enough to melt lead. The explanation lies in orbital mechanics. Unlike Earth, Mercury has virtually zero axial tilt. Because the planet sits perfectly straight up, the Sun never rises above the horizon at the extreme northern and southern poles. This straight axis creates permanently shadowed craters. Inside these deep impact basins, temperatures plunge to negative 290 degrees Fahrenheit and have remained locked at that temperature for billions of years. This radar image of Mercury's North Pole region shows bright, highly reflective deposits clustered exactly inside those shadowed craters. Observations confirm these signals indicate massive deposits of water ice and organic compounds. The leading theory is that these volatile materials were delivered over eons by ancient, water-rich comets impacting the planet's surface. By trapping these comet fragments in permanent darkness, Mercury operates as a perfect cosmic freezer, preserving the ancient, icy building blocks of the solar system mere miles from the Sun's incinerating heat. These paradoxes force a total reassessment of the entire inner solar system. The data generated radical new theories. Mercury's bizarre metallic composition hints that it may have actually formed much further from the Sun and migrated inward over time, or that it lost its entire outer mantle in a catastrophic ancient collision. All of this points to one critical, unanswered question. How do rocky, Earth-like planets actually form and survive in the chaotic, violent zone closest to a star? To find the answer, the European and Japanese space agencies partnered for the launch of the Bepi-Colombo mission. The Bepi-Colombo spacecraft uniquely consists of two separate orbiters designed to detach upon arrival. While one probe maps the chemical composition of the surface, the other monitors the dynamic magnetosphere, capturing synchronized data from two different vantage points. By studying Mercury's unique environment, scientists are gathering the missing pieces needed to understand the violent conditions under which the inner planets, including Earth, took shape. $4.5 billion years ago, the solar system produced two nearly identical rocky worlds. They shared the same size, mass, and elemental makeup. Because of these similarities, early 20th century astronomers assumed the planets shared a climate too. Peering through telescopes at the thick, opaque clouds obscuring Venus, scientists hypothesized a planetary greenhouse, imagining a wet, rainy world covered in dense jungles. The reality remained hidden until the Soviet space program launched the Venera probes, sending heavily armored landers to pierce the cloud cover and touch down on the surface. The sensors transmitted data describing a lethal environment. Surface temperatures hovered around 460 degrees Celsius, hot enough to melt lead. The atmospheric pressure was 92 times that of Earth's sea level, crushing and destroying the armored landers within minutes. Before their electronics cooked, a few probes managed to transmit grainy photographs back to Earth. They revealed a barren, fractured landscape of sharp rocks beneath a dim, sulfur-yellow sky. Yet modern computer modeling of the planet's ancient climate reveals a different past. These simulations suggest that Venus likely harbored a shallow liquid water ocean and habitable temperatures for up to 2 billion years. Learning how a temperate, watery twin devolved into a high-pressure furnace remains a major objective for planetary scientists, a test case for the stability of habitable environments across the solar system. The divergence between the two planets began with their physical location. Orbiting closer to the Sun, the young Venus received about 40% more solar radiation than Earth. This process triggered an evaporation loop. As the young Sun warmed, the surface water on Venus began to evaporate, turning into water vapor, a potent greenhouse gas capable of trapping more heat. The increased vapor raised temperatures further, which in turn accelerated the evaporation rate. This runaway greenhouse effect compounded on itself until the planet's oceans boiled completely dry. The resulting water vapor drifted into the stratosphere. There, intense ultraviolet light from the Sun bombarded the molecules, shattering the chemical bonds and splitting the water into free oxygen and hydrogen. At this point, the remaining water vapor combined with carbon dioxide to form an abundant ion known as HCO+. When these HCO+ molecules recombined and broke down, the chemical reaction violently ejected the lighter hydrogen atoms. They achieved escape velocity and bled out into space, permanently deleting the planet's water inventory. The total depletion of water had consequences far beyond the atmosphere. It removed a critical lubricant required for the planet's internal geological movement. On Earth, liquid oceans facilitate the movement of tectonic plates, while rainfall actively scrubs carbon out of the atmosphere, weathering it back into the planet's crust. Without water to lubricate these processes, the Venusian tectonic system lost its mobility. The global plate mechanics seized up, locking the planet inside a thick, stagnant crust. Heat continued to build in the mantle, with no tectonic vents to release it. Eventually, this thermal stress fractured the locked crust, triggering planet-wide volcanic eruptions that baked the planet's entire carbon budget directly into the sky. Today, that carbon forms a crushing, hyperdense atmosphere composed of 96.5% carbon dioxide, topped by thick clouds of concentrated sulfuric acid. This cross-section maps the current atmospheric wind speeds. While the air at the surface is nearly still, the upper cloud layers experience superrotation, whipping around the planet at over 100 meters per second, 60 times faster than the planet rotates. Driven by solar thermal tides, This super-rotating atmosphere circles the globe every 4 days. It acts as an aggressive convection engine that equalizes temperature perfectly across both the day and night sides of the planet. A paralyzed, immobile crust, combined with a hyper-rotating, carbon-choked atmosphere, created a self-sustaining planetary furnace. This ancient cataclysm destroyed the planet's habitability, but modern observations suggest the surface may not be completely dead. To investigate, NASA launched the Magellan spacecraft to map the hidden, deformed crust of the planet using synthetic aperture radar. This global radar map exposes the entire topography of the planet. Beneath the clouds lies a landscape scarred by massive rifts and thousands of individual volcanoes. Looking closer at this perspective view, the presence of a large impact crater and sprawling volcanic domes provides a direct physical record of the planet's geological history. Recently, scientists reanalyzed archival data from the Magellan mission and identified surface changes that prove volcanoes on Venus are still actively erupting today. Other mysteries remain. Recent spectral observations suggest the presence of phosphine gas deep within the temperate cloud deck, a chemical signature that on Earth is typically produced by biological life. To investigate these anomalies, space agencies are preparing a new armada of robotic explorers. In the coming decade, missions like Veritas, Da Vinci Plus, Envision, and Shukran-1 will return to sample the atmospheric chemistry directly. Studying the death of Earth's twin is a direct investigation into the limits of habitability. The data hidden beneath the clouds of Venus provides the physical evidence required to understand the fragile balance keeping our own world stable. Four and a half billion years ago, Earth was a hostile, partially molten sphere. A massive atmosphere of steam and carbon dioxide smothered a surface in constant turmoil, heavily bombarded by comets and meteoric debris. Into this volatile environment, a Mars-sized protoplanet known as Thea collided directly with the proto-Earth. The extreme energy of this collision vaporized outer silicates and sent a massive debris disk into orbit, which eventually coalesced to form the Moon. The impact also dictated Earth's axial tilt and supplied the high angular momentum that drives the rotation of our modern Earth-Moon system. This near-fatal collision provided the mechanical stability required for a predictable planetary environment to take shape. Over the next 20 million years, the intense heat radiating from the mantle began to dissipate. The surface cooled rapidly on a geological timescale, allowing the global magma ocean to freeze into a solid planetary crust. As surface temperatures continued to drop, the dense steam atmosphere condensed. Torrential rains fell for millennia, creating a continuous global ocean of liquid water. This early water world was highly toxic. The oceans and atmosphere were entirely devoid of free oxygen, relying on a dense methane greenhouse effect to trap solar radiation and prevent the planet from freezing solid. Far from a hospitable paradise, the early Earth was a dormant crucible, waiting for a biological catalyst to trigger the next phase of its evolution. That catalyst appeared roughly 2.4 billion years ago. A microscopic organism known as cyanobacteria evolved a method for generating energy using sunlight and water. In early photosynthesis, cyanobacteria processed water and light, releasing highly reactive oxygen as a continuous waste byproduct. This oxygen diffused out of the oceans and accumulated in the sky, where it displaced the methane molecules forming the planet's thermal blanket. With the methane layer stripped away, the planet lost its primary greenhouse gas. Global temperatures plummeted, locking the Earth into its first massive period of glaciation. By extracting energy from sunlight and water, early life inadvertently poisoned the atmosphere, destroying its own climate and nearly sterilizing the planet in a global freeze. Geological mechanisms eventually exerted their own influence on the atmosphere. Around 717 million years ago, the supercontinent Rodinia fragmented into smaller landmasses positioned near the equator. During silicate weathering, the fractured continent exposed fresh volcanic basalt. These massive rocks chemically absorbed downward-flowing carbon dioxide, permanently locking it into stone. This continuous CO2 drawdown weakened the greenhouse effect, causing polar ice sheets to advance and create a snowball Earth. The physical shifting of tectonic plates proved massive enough to overpower the atmosphere, forcing the entire globe into a deep freeze. Beneath the miles-thick ice, tectonic activity continued. Over millions of years, volcanic eruptions steadily pumped carbon dioxide back into the atmosphere, unable to be absorbed by the ice-covered rock. Once the trapped greenhouse gases reached a critical density, they forced a rapid global thaw. The equatorial ice sheets violently fractured and collapsed into the ocean, creating extreme fluctuations in oceanic chemistry and temperature. This massive thaw washed staggering amounts of weathered minerals, phosphates, and calcium into the sea. These rising nutrients, combined with a sudden oxygen pulse, provided the chemical raw materials for biomineralization, allowing life to produce the shells and complex skeletons found in the Cambrian explosion. The transition from a frozen world to a mineral-rich, oxygenated ocean created the precise chemical environment necessary for the rise of complex animal life. Even as the oceans filled with diverse predators 428 million years ago, the exposed continents remained completely barren, lifeless expanses of solid rock. That division ended with the Silurian-Devonian terrestrial revolution, an aggressive colonization of dry land led by early fungi and deep-rooted vascular plants. Expanding plant roots exerted immense mechanical pressure, penetrating solid bedrock to create the pedosphere, Earth's first mineral-rich soil. This spreading flora triggered a severe atmospheric feedback loop, pulling massive quantities of carbon dioxide from the air while simultaneously pushing oxygen to near-modern levels. Fertile soil and breathable air are not inherent planetary features. They are biological products, engineered over eons by early plant life. With an oxygen-rich atmosphere and continents blanketed in nutrient-dense soil, the land could finally support complex fauna. Early arthropods and tetrapods emerged from the water to breathe air and populate the continents. The vibrant blue and green Earth that we instantly recognize today is merely the current equilibrium of these ancient feedback loops. Earth functions as a co-evolutionary engine. The mechanical movement of the crust and the metabolic cycles of life exist in a state of continuous mutual reconfiguration. $4.5 billion years ago, a Mars-sized body collided with Earth. The resulting debris accumulated in orbit, fusing to form our natural satellite. Over time, the friction of Earth's gravity forced the Moon into synchronous rotation. Because its orbital period matches its rotation, the two bodies are tidally locked, meaning we only ever see this single, heavily cratered, near-side hemisphere. Despite sitting an average of 238,000 miles away, the Moon exerts a continuous physical force on our planet, constantly pulling on Earth's oceans. Gravity creates an elliptical water bulge. As Earth rotates, coastlines pass through this bulge, causing daily tides. During a new or full moon, the Sun and Moon's gravity align, stretching the water further to produce extreme spring tides. The Moon operates as an active mechanical engine. Its gravitational drag moderates Earth's wobble, stabilizes our climate, and continually shapes our physical coastlines. For most of human history, that physical distance made the Moon an untouchable canvas. Early observers mapped its surface with telescopes, assigning Latin names to its features, and filling the empty spaces with their own imaginations. Looking closely at the dark impact basins, or Maria, people across the world recognized the silhouette of a rabbit. This image of a moon rabbit appears prominently in Aztec folklore, in ancient Chinese mythology, and in Japanese cultural legends. While the specific legends vary, from pounding medicine to making rice cakes, these distinct civilizations developed strikingly similar visual interpretations independently, without ever having contact with one another. Stargazers separated by thousands of miles projected identical motifs onto the night sky. Long before aerospace engineering made the journey possible, a shared global urge existed to connect with the lunar surface. In the mid-20th century, the moon came within physical reach. Cold War competition accelerated aerospace engineering, turning an object of myth into a strategic high ground. The Soviet Union secured early robotic victories. Their Luna probes captured the first photographs of the lunar far side and successfully returned the first robotic soil samples to Earth. The United States answered with the Apollo program, landing humans directly on the arid, flat equatorial plains. During these landings, Apollo astronauts collected 842 pounds of lunar rock and soil, bringing physical pieces of the moon back to laboratories for analysis. Scientists tested these samples and found them to be entirely devoid of moisture. The scientific consensus concluded the moon was a dead, bone-dry world. Without local water to sustain long-term missions, the logistical cost of hauling supplies out of Earth's gravity well was too steep. The momentum for lunar exploration stalled, and human missions stopped for over 50 years. Decades later, planetary scientists realized the Apollo astronauts brought back dry rocks because they landed in sunlit equatorial regions, where daytime temperatures boil away any volatile compounds. Modern observation tools updated the consensus. In 2020, NASA's airborne SOFIA observatory, flying above Earth's atmospheric interference, detected water molecules distributed directly across the sunlit lunar surface. This animated cross-section reveals a concentrated target, cold traps. These deep craters at the lunar south pole stay in permanent shadow, with temperatures plummeting to -256°F. Over billions of years, these frozen pockets have perfectly preserved water ice delivered by passing comets. The moon serves as a multi-billion-year-old fault, preserving the water ice necessary to sustain long-term human biology and power the next generation of spacecraft. The modern rush to locate this lunar water serves an industrial purpose. While astronauts need water to survive, these vast polar deposits are targeted for heavy manufacturing. The strategy centers on in situ resource utilization, or ISRU. This engineering practice relies on harvesting and processing local materials to sustain a mission, rather than launching expensive payloads from Earth. This diagram outlines the chemistry of ISRU. By applying electrical energy, frozen lunar water can be split into hydrogen and oxygen. The hydrogen serves as high-efficiency rocket propellant, while the oxygen provides breathable air for habitats. Manufacturing propellant locally turns the moon into a deep space refueling station. Launching a fully fueled vehicle from the moon's low gravity makes onward missions to Mars economically viable. This economic reality has ignited a fierce contemporary space race. Global space agencies and international coalitions are actively competing to claim and extract the resources clustered at the lunar South Pole. China's upcoming Chang'e 7 mission will deploy a specialized hopping robot to dive directly into permanently shadowed craters to drill for ice. Subsequent missions will test the feasibility of 3D printing construction bricks from lunar regolith. These robotic missions lay the technical foundation for the International Lunar Research Station, a cooperative surface base planned for construction in the 2030s. Meanwhile, the United States is advancing the Artemis program. Powered by the Space Launch System, Artemis targets consecutive crewed landings at the lunar South Pole. NASA and its international partners intend to execute yearly lunar landings. The objective of Artemis is to establish a permanent, enduring base camp on the surface. The craters, once shrouded in folklore, have become the foundation of our industrial future. Now, human exploration is moving beyond temporary landings to establish the first durable outpost on the lunar frontier. Stand on the surface of Mars today, and you are surrounded by a freezing, hyper-arid desert beneath a butterscotch-colored sky. The baseline conditions here are highly hostile. The global temperature averages -85°F. The atmosphere is so thin, measuring just 1% the density of Earth's, that any liquid water exposed to the surface would simultaneously boil and freeze. Yet this dead landscape is dominated by physical features of monumental scale. Olympus Mons rises from the crust as the tallest volcano in the entire solar system. A vast canyon system, Valles Linearis, fractures the equator. It stretches over 2,400 miles long and descends nearly 6 miles deep, dwarfing Earth's Grand Canyon by a factor of 10 in both length and width. This frozen geography is a direct symptom of extreme planetary physics, leaving behind an immense geological mystery. If you look closely at this dusty terrain today, you will find the physical scars of a highly active hydrological past. The surface shows scalloped topography, with teardrop-shaped islands and intricate branching river valley networks. This satellite image captures the Birdfoot Delta inside the Eberswald crater. These meandering, laterally accreting channels are identical to river deltas on Earth, proving that persistent, fast-moving rivers once emptied into standing lakes. We are looking at a world carved by violent rivers and vast oceans, yet it exists in a state where liquid water cannot survive. To understand what happened, we have to look back 4 billion years to the Noachian epoch. Early Mars was a warm, volcanic pressure cooker, covered by a high-temperature global ocean and wrapped in a thick atmosphere. But Mars had a structural flaw. Its mass is only 11% of Earth's. It simply lacked the physical bulk required to insulate its internal heat over billions of years. Because of this smaller size, the molten Martian core rapidly cooled and solidified. When the core stopped churning, the planet's magnetic dynamo shut down. Without that magnetic force field, the upper atmosphere was left totally exposed. High-velocity waves of solar wind impacted the planet directly, systematically stripping the primordial atmosphere and blowing its particles out into space. The loss of the planet's internal heat was the primary trigger that permanently destroyed its habitable surface environment. As the atmospheric pressure plummeted, the global oceans could no longer remain liquid. They evaporated into space or retreated deep underground, locking into the crust as permafrost. Today, the trace carbon dioxide that remains provides zero thermal insulation. If you were to stand on the Martian equator at noon, the temperature stratification would be severe. It would be 75 degrees Fahrenheit at your boots and a freezing 32 degrees at your helmet. The climate is further destabilized by the planet's highly elliptical orbit. With an eccentricity of 0.093, the distance between Mars and the Sun varies wildly, creating intense, asymmetrical seasonal shifts. These extreme orbital temperature swings generate massive thermal winds. As these currents sweep across the dry surface, they kick up iron oxide dust, suspending it in the atmosphere and scattering red light to create that distinct butterscotch-colored sky. The modern Martian climate operates entirely at the mercy of its erratic orbit and its lack of atmospheric armor. When the internal heat died and the liquid water vanished, the processes of plate tectonics and chemical erosion completely stopped. Mars became a static geological museum. This explains the massive scale of features like Olympus Mons. Because the planetary crust stopped moving, magma simply erupted from the exact same stationary vent for millions of years, piling up into an enormous shield. But the water isn't entirely gone. Massive permafrost sheets cover the polar caps, and radar scans have detected large bodies of subglacial liquid water hidden deep beneath the surface. Today, Mars operates as a perfectly preserved graveyard of a once living world. This dead planet offers a strict lesson in planetary mortality. It illustrates the exact fragile balance of mass, heat, and magnetism required to sustain a habitable environment. Because this history is so perfectly frozen in place, Mars has become the primary destination for a targeted series of robotic arrivals. Missions like India's upcoming Mangalyaan 2 and NASA's ESCAPE-8 satellites are being sent to investigate this undisturbed geological record. The exact same harsh, frozen conditions that killed the Martian surface billions of years ago are what protected it, leaving a readable map of how planets live and die. Between the orbits of Mars and Jupiter lies a vast ring of debris. Millions of dry, rocky remnants drift through this space, left over from the early construction of the solar system. Yet one object defies the profile of a standard asteroid. It is massive enough to account for a full third of the entire belt's weight. When Italian astronomer Giuseppe Piazzi first spotted the anomaly in 1801, he was trying to map what he thought was a missing planet. The celestial body was named Ceres, honoring the Roman goddess of agriculture, a fitting title for an object nestled among a sprawling field of rocks. Centuries later, astronomers utilized orbiting observatories to precisely measure its exact dimensions. They found that Ceres possessed enough gravity to pull its own mass into a nearly perfect sphere. That spherical shape, combined with its immense mass, meant it could no longer be grouped with the irregular rubble surrounding it. In 2006, the astronomical community formally designated Ceres as a dwarf planet. To understand this massive outlier, NASA launched the Dawn spacecraft. For years, scientists prepared for its arrival and orbital insertion. Prior to 2015, the best images of Ceres were barely more than pixelated blurs. As dawn approached, the true surface finally came into focus. Mapping the dark, heavily cratered terrain, the cameras captured an intense reflection. Deep inside the Ocator crater, a cluster of blindingly bright patches was suddenly glowing against the dark rock. Exposed ice cannot survive long on the surface here. The daytime temperatures at the equator reach -30 degrees Celsius, far too warm to prevent water ice from sublimating into space. Finding highly reflective material persisting on the surface indicates an active process. Something inside this dark, quiet rock is pushing fresh material into the vacuum of space. Dawn lowered its orbit to inspect the brightest of these regions, Cerealia Facula and Venalia Faculae. The spacecraft's spectrometers analyzed the light reflecting off the basin. The signatures did not match pure ice. Instead, they revealed highly reflective sodium carbonate salts. These salt deposits are the visible scars of a process driven by sublimating brines. Deep underground, escaping gases push pockets of salty water up through fractures in the crust. When that fluid hits the vacuum of space, it instantly boils away into vapor. The water is gone, leaving only a bright, crystalline salt crust. These ascending fluids also construct massive vertical features. Dawn mapped Ahuna Mons, a cryovolcano built from erupting and freezing brines instead of molten rock. The data also showed high concentrations of aliphatic organic molecules near Uranus crater, confirming that complex carbon compounds are mixing within this salty environment. Fresh salt deposits, active ice volcanoes, and carbon organics mark Ceres as an evolving world rather than a static graveyard. To map the architecture driving this activity, scientists analyzed the subtle gravitational pulls on the Dawn spacecraft to calculate global density. Ceres is highly differentiated, with distinct internal zones. It is 25% water ice, forming an outer crust surrounding a dark, muddy mantle and rocky core. The erupting fluids source from deep within, trapped in a porous boundary layer where the mantle meets the icy crust. This layered anatomy identifies Ceres as a relict ocean world, a frozen snapshot of a planet that once contained a vast reservoir of liquid water. To see that ocean at its peak, we have to rewind the clock between 2.5 and 4 billion years. During its early formation, Ceres possessed a powerful internal heating mechanism. Its dense rocky core contained finite radioactive elements. The decay of those isotopes acted exactly like a furnace, pushing the core temperature to 800 Kelvin. That heat radiated outward, sustaining a warm, global subsurface ocean for hundreds of millions of years. The intense hydrothermal activity mixed the hot, dissolved minerals with carbon molecules, producing a massive repository of chemical energy. This ancient, energy-rich environment challenges the assumption that habitable conditions are exclusive to the moons of gas giants. One final chemical anomaly remains on the surface. Spectrometers detected ammonia salts, compounds that are too volatile to survive the heat of the inner solar system, where Ceres currently resides. This suggests Ceres is a migrant. It likely formed in the freezing outer reaches of the solar system, before Jupiter's massive gravitational shifts deflected it inward to the asteroid belt. Despite a violent nomadic history and a current state of deep freeze, the dwarf planet has preserved its chemical legacy just beneath a shell of rock and ice. As the most accessible ocean world in our solar system, Ceres preserves the ancient building blocks of life, awaiting a future sample return mission to reveal the history of its interior. For centuries, the standard model of planet formation was simple. Dust and gas coalesced in stable rings, gradually accreting into the planets we see today, all remaining largely in the orbits where they were born. But this chart shows a stark contrast between our solar system and the exoplanet systems we observe across the galaxy. Most star systems are packed with massive super-Earths huddled close to their host star. Our inner system features a sparse distribution of relatively small rocky planets, an unusually tiny Mars, and a highly depleted asteroid belt. To explain this architecture, astronomers developed the Grand Tack hypothesis. It proposes that early in the solar system's history, a young Jupiter migrated inward through the protoplanetary gas disk. Traveling as close to the Sun as Mars's current orbit, Jupiter's massive gravity scattered planetary building blocks, clearing out most of the solid material in the inner solar system. Jupiter would have continued spiraling into the Sun if not for the formation of Saturn. As Saturn grew and migrated inward, the two gas giants locked into an orbital resonance. This gravitational tether reversed Jupiter's course, and the pair dragged back outward to their current positions. This inward and outward migration truncated the inner disk of material. It starved Mars of the debris it needed to grow larger, while leaving just enough concentrated material at 1 astronomical unit for the formation of Earth. Verifying the dynamics of this cosmic sculpture meant we had to examine its internal mechanics firsthand. That required launching dedicated probes, like the Galileo spacecraft, to study the giant at close range. More recently, the Juno mission arrived to measure the planet's gravitational and magnetic fields. By plunging through thick, colorful cloud bands into the dark, crushing pressures below, Juno sent back data that overturned long-held assumptions about gas giants. The planet that cleared the path for Earth's survival is governed by internal physics entirely different from textbook predictions. Descending 43,000 miles to the absolute center of Jupiter, astronomers long assumed they would find a dense, solid core of rock and ice, roughly the size of Earth, sharply separated from the gases above. Precision gravity measurements mapped by the Juno spacecraft proved that discrete rocky sphere does not exist. This diagram illustrates the new consensus, a dilute or fuzzy core. Heavy elements are distributed across a massive portion of the deep interior, forming a partially dissolved mix of material that blends seamlessly into the layers above, without a distinct physical boundary. Moving outward from this diffuse center, the pressure drops slightly, but remains immense. Here, the crushing weight of the atmosphere above forces hydrogen gas into a continuous, churning liquid ocean. Deeper within this ocean, the pressure becomes so extreme that electrons are squeezed away from their hydrogen atoms. The hydrogen transitions into a metallic, electrically conductive fluid. Because Jupiter completes a full rotation on its axis every 10 hours, this metallic ocean is constantly swirling and convecting. The massive rotating volume of conductive fluid acts as a planetary dynamo. This churning metallic engine hidden deep within the planet generates the immense forces that dictate Jupiter's violent exterior and project its influence millions of miles into the solar system. Rising back up through the metallic ocean, we reach the upper atmosphere, characterized by extremely cold, windy cloud decks, composed primarily of ammonia and water vapor. Jupiter's rapid rotation stretches these clouds into the signature dark belts and bright zones. Embedded within these bands are enormous storms, like the Great Red Spot, which have maintained their structure for over 3 centuries. For generations, astronomers debated whether these vibrant bands and spinning ovals were thin, superficial weather patterns drifting across the cloud tops, or if they were deeply rooted in the planet's interior. Juno's microwave instruments peered beneath the visible layers and revealed that these structures are colossal vertical pillars. The Great Red Spot is a massive vortex extending over 200 miles downward, plunging well below the depth where sunlight penetrates or water clouds form. The probes also mapped polygonal polar cyclones at the planet's extremes. At the North Pole, 8 massive storms remain locked in a remarkably stable octagonal pattern, continuously pushing against a central polar cyclone without merging. The complex, beautifully chaotic weather visible through our telescopes is merely the surface exhaust of a deep, vertically integrated atmospheric machine powered by Jupiter's internal heat. That internal power extends far beyond the visible cloud tops. Jupiter generates an immense magnetosphere that balloons up to 3 million miles toward the Sun and trails outward as far as Saturn's orbit. This massive field is roughly 20,000 times stronger than Earth's, completely reliant on the spinning metallic hydrogen dynamo turning deep within the planet's core. Trapped deep within this intense magnetic environment is Io, the most volcanically active body in the solar system. Io ejects 1,000 kilograms of sulfur and oxygen gas every second. Jupiter's magnetic field traps it in the donut-shaped Io plasma torus. Jupiter's fast rotation forces this plasma into co-rotation. Centrifugal force stretches the torus radially, flattening into a wide, intensely radioactive magnetodisk. Moving outward through these radiation belts, we encounter Europa and Ganymede. In stark contrast to Io's dry, rocky surface, these moons are sheathed in thick, icy crusts that conceal global oceans of liquid water. This sharp difference in composition is an outcome of their formation. Thermodynamic modeling shows this architecture was set at birth. Io formed in the high-temperature zone near the young Jupiter, where water could not condense, while Europa and Ganymede accreted beyond the circumplanetary ice line. To characterize these ocean-bearing moons and assess their potential to harbor life, space agencies are deploying probes like the ESA JUICE spacecraft, equipped with the most powerful payload ever sent to the outer solar system. Jupiter acts as a massive planetary engine that violently cleared the path for our own world to thrive. Today, its system of complex, varied moons serves as our greatest laboratory for understanding the mechanics of habitable environments across the universe. "500 million miles from the Sun, Jupiter is surrounded by a lethal radiation belt. Inside this storm sits a frozen moon, Europa. Its surface is a desolate wasteland of cracked water ice, where temperatures regularly plunge to 370 degrees below 0 Fahrenheit. The equatorial regions of this moon are likely covered in a massive forest of jagged ice spikes. In a frigid vacuum, ice turns directly into vapor, carving the surface into treacherous blades that can tower 15 meters high. If a spacecraft tried to touch down here, it would have to navigate those enormous spikes while being continuously bombarded by Jupiter's crushing radiation. Europa presents one of the most hostile, impenetrable physical barriers in the entire solar system. In the late 1990s, NASA's Galileo spacecraft reached the Jovian system to begin a multi-year survey of the moon's physical properties. As Galileo passed by, its instruments measured Jupiter's magnetic field bending around Europa. Something inside was interfering. That magnetic signature is the hallmark of a highly conductive fluid, proving that beneath the crust lies a massive global ocean of salty liquid water. This hidden sea is so vast that it holds roughly twice as much liquid water as all of Earth's oceans combined. The solar system's most promising sanctuary for extraterrestrial life is trapped directly underneath a lethal frozen barrier. But that deadly radiation environment on the surface is highly active chemistry at work. Recent measurements from NASA's Juno spacecraft show that as high-energy charged particles constantly slam into the moon, they shatter the bonds of the surface water molecules, splitting them apart. This relentless bombardment manufactures approximately 12 kilograms of life-sustaining oxygen every single second. The very radiation that makes the exterior so deadly is running a massive chemical factory, producing a critical ingredient required to support life. The challenge is getting that oxygen down into the water. It has to bypass a solid ice shell that is 10 to 15 miles thick. Europa experiences intense tidal flexing from Jupiter's gravity. This immense stress causes the ice shell to groan and crack, behaving much like plate tectonics. This continuous churning points to crustal delamination. Pockets of surface ice, heavy with oxygen, weaken under stress, and sink slowly through the softer ice below. Acting as a geological conveyor belt, they reach the ocean boundary, releasing their payload into the water. Europa's icy barrier operates as a dynamic, moving transport system, bridging the irradiated surface and the sheltered sanctuary below. Down in the ocean itself, the water stretches between 40 and 100 miles deep. In this absolute pitch-black abyss, sunlight cannot penetrate, which rules out photosynthesis entirely. But at the very bottom of this deep sea, the liquid water is in direct contact with Europa's rocky silicate mantle. The same intense tidal friction that violently cracks the icy surface above also generates massive heat within the rocky core below. This internal friction likely powers hydrothermal vents along the seafloor, injecting a dark, billowing plume of raw chemical energy and minerals straight into the water. With a vast liquid ocean, a steady supply of oxygen, and heat from volcanic vents, the essential prerequisites for life have converged in the dark. Those 15-meter surface spikes and the lethal radiation make a traditional landing nearly impossible. To explore this ocean, we need a completely different strategy. Our next steps rely on an orbital armada. NASA's Europa Clipper, seen here lifting off to begin its journey, will arrive in 2030, followed closely by the European Space Agency's JUICE mission in 2031. To survive the Jovian system, Clipper is heavily armored. Its delicate electronics are sealed inside a thick vault of titanium and aluminum, built to withstand the intense radiation long enough to collect data. Rather than entering orbit around Europa directly, Clipper will perform 49 sweeping flybys. On each pass, it will use ice-penetrating radar to look straight through the frozen crust and map the structure of the ocean beneath. The spacecraft is also equipped with highly sensitive spectrometers. If Europa vents water vapor into space through cracks in the ice, Clipper will fly through the plumes, physically tasting the ocean's chemistry from miles above the surface. This orbital approach allows us to map the interior and sample the ocean's chemistry without ever having to touch the hazardous terrain below. When we pull back and look at the ultimate stakes of these missions, we are testing the boundaries of biology itself. As Clipper and JUICE confirm that this deep ocean is habitable, it proves that biological ecosystems do not require a warm, sunlit surface to thrive. If life can exist in the dark, irradiated, ice-sealed abyss of Europa, the universe may be teeming with hidden oceans, expanding our map of where we might find company in the cosmos. For centuries, humanity looked through early telescopes and saw a perfectly smooth, pastel-colored jewel suspended quietly in the dark. But the closer our spacecraft get, the more that illusion of peace falls apart. This is a violently dynamic, chaotic environment. Those solid-looking rings are actually a high-speed demolition derby, where billions of ice and rock fragments shatter and collide at thousands of miles an hour. Beneath them, the calm atmosphere is a roiling cauldron of extreme weather, driven by supersonic winds. Saturn's gravitational grip holds over 140 moons in a complex, interconnected web of worlds. To find the source of that power, we have to drop directly into the depths of the giant itself. The rings spanning out from the planet are composed of 90 to 95% pure water ice. The debris ranges from microscopic grains of dust to boulders the size of houses. This diagram illustrates the constant physics equation acting on every single particle in the ring field. Saturn's immense gravity attempts to pull the ice inward, while the sheer speed of their orbital velocity tries to fling them out into deep space. As small moons pass through or near the rings, their own gravity actively sculpts the material, carving out wide gaps and dragging the ice into elongated clumps and towering vertical ridges. Even at the microscopic level, the environment is unstable. Ultraviolet radiation from the sun and constant micrometeoroid impacts strip electrons from the tiny dust particles, giving them an electrical charge. Once charged, that delicate balance of forces breaks. The particles become susceptible to Saturn's magnetic field, following its curved lines to rain down directly into the planet's upper atmosphere. The rings we see today are temporary. They are structures defined by a continuous cycle of creation and active decay. Dropping below the rings and into the cloud tops, the environment grows even more hostile. At the equator, winds whip around the globe at 1,100 miles per hour, the second fastest atmospheric currents in the solar system. Moving up to the North Pole reveals a massive, persistent geometric storm known as the hexagon. It spans 20,000 miles across and cuts 300 miles deep into the atmosphere. Fluid dynamics simulations suggest this shape is a standing wave. Deep atmospheric currents essentially pinch an intense horizontal jet stream, forcing the winds into a stable, six-sided geometric wave. The entire hexagon rotates in perfect synchronization with the radio emissions generated by Saturn's interior, proving the storm is physically anchored to the deep internal rotation of the planet. If a probe were to keep descending past these storms, the temperature and pressure would rise until the gases compress into a liquid. There is no solid surface to land on. Instead of a hard, rocky center, the latest data points to a fuzzy core. Hydrogen and helium gas gradually mix with an increasing density of ice and rock, similar to how ocean water gets saltier the deeper you dive. The pastel clouds visible from Earth completely mask a crushing, fluid interior with some of the most bizarre structural physics we have ever observed. Pulling away from the crushing gravity of the gas giant, we find a sprawling network of icy moons. One in particular, a small world named Enceladus, commands attention. Because of its elliptical orbit, Saturn's massive gravity physically stretches and squeezes Enceladus. This friction generates immense internal heat, a process called tidal heating, which melts the interior enough to sustain a global liquid water ocean beneath the ice. At the moon's south pole, hydrothermal vents shoot jets of water, complex organic compounds, and mineral-laced ice grains straight out into space. Those erupting geysers act as a cosmic fountain. The expelled ice grains spread out along the moon's orbit, directly creating and sustaining Saturn's diffuse outermost E-ring. Further out sits Titan, a moon larger than the planet Mercury. It holds the distinction of being the only moon in our solar system with a thick, dense atmosphere and stable, liquid hydrocarbon lakes on its surface. Observational, the exact same gravitational forces that create deadly, crushing pressures inside Saturn are acting as the thermal engines for prebiotic chemistry on its moons. Our exploration of this system is about to transition from distant orbital photography to direct powered flight through an alien atmosphere. This is Dragonfly, a nuclear-powered robotic rotorcraft currently being engineered to fly across Titan's organic sand dunes and analyze its prebiotic chemistry. Scheduled to launch in 2028, it will spend 6 years cruising through the solar system to search for the chemical precursors to biology. The Saturnian system presents a rare juxtaposition. The same physics and fluid dynamics that crush spacecraft also maintain the thermal balances required for life. The most hostile, turbulent planet in our neighborhood has become a vital and promising frontier in the search for extraterrestrial life. Out here in the outer solar system, almost 1 billion miles from the Sun, temperatures plunge to a fraction of a degree above absolute zero. Most of the moons orbiting Saturn are silent, frozen monuments. But buried within the planet's massive ring system is a blindingly white sphere that defies the physics of its environment. Enceladus is barely 300 miles across. Its surface temperature hovers around -330 degrees Fahrenheit. By all conventional planetary models, a body this small and this cold should be completely inert. To put that into perspective, if you place Enceladus next to our own moon, it is roughly 1/7 the size. It is a cosmic speck. Because of those tiny dimensions and an icy crust that reflects almost all incident sunlight back into space, Enceladus lacks the mass to retain internal heat. Standard physics dictate it should be a solid block of frozen rock and ice all the way to its core. The Cassini mission arrived at Saturn in 2004 with a mandate to survey the entire system, from the massive rings to the smallest satellites. But during its initial flybys, Cassini's instruments picked up a strange magnetic disturbance. Something invisible, erupting from this tiny moon, was physically pushing back against Saturn's massive magnetic field. Cassini turned its cameras toward the source of the disturbance at the moon's south pole. Instead of a heavily cratered ancient landscape, the images revealed a smooth surface of fresh ice. The terrain was geologically young and actively shifting. Carved directly into this ice were 4 massive parallel fissures. Researchers named them the Tiger Stripes. This map shows the infrared thermal data collected from that region. Against the backdrop of the deep freeze, those 4 fissures were glowing with intense heat, radiating from deep within the canyons. That heat powers a continuous physical eruption. Violent jets of water vapor and ice particles blast out of the stripes and into the vacuum of space at 800 miles per hour. The output is so massive that these geysers single-handedly supply the icy material that forms Saturn's broad, diffuse E-ring. Enceladus is not a dead rock. It is a violently active world venting its internal anatomy into space. The discovery forced a new question. What exactly is hiding beneath that crust? To find the source of that power, we have to look down through the ice, deep into the fissures. The engine driving this activity is a process called tidal heating. As Enceladus orbits, the immense gravitational pull of Saturn physically stretches and squeezes the moon. This continuous mechanical flexing creates friction deep inside the moon. That friction generates heat, which melts the ice from the inside out. The result is a vast global ocean of liquid water, permanently trapped beneath 12 to 16 miles of solid ice. This hidden sea is roughly 10 miles deep. Despite the moon's tiny footprint, that ocean holds about 2% of the total volume of all the oceans on Earth combined. Liquid water is the absolute foundational requirement for life as we know it. Thanks to the constant pull of Saturn, Enceladus has maintained this massive, protected reservoir for billions of years. At the very bottom of the Enceladian Ocean, the liquid water meets a porous, rocky core. When Cassini analyzed the erupting plumes, it found nanoscale silica grains, particles that only form when water and rock interact at temperatures above 200 degrees Fahrenheit. This confirms the sea floor of Enceladus is dotted with active hydrothermal vents, remarkably similar to deep-sea ecosystems found in the darkest trenches of Earth's oceans. As mineral-laden fluid blasts from the core, vents continuously release molecular hydrogen into the water. On Earth, certain microbes consume hydrogen as a direct source of metabolic energy, allowing complex ecosystems to thrive without a single drop of sunlight. Enceladus satisfies the second crucial requirement for biology, a potent energy source operating in the dark. That heated, mineral-rich water rises from the rocky seafloor, travels up through 10 miles of ocean, and is forcefully ejected out of the icy crust. Cassini analyzed the chemical makeup of this ejected water and found it loaded with complex macromolecular organics, the heavy carbon chains necessary for biology. This list represents the 6 essential elements required for all life on Earth, known collectively as CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. In 2023, researchers identified the final missing element, confirming that abundant phosphorus is locked inside the moon's salt-rich ice grains. Phosphorus is the critical linchpin. It's the structural backbone for DNA, as well as for RNA, and the cell membranes that allow life to function. With the liquid solvent, the hydrothermal energy source, and the complete biogenic chemical inventory confirmed, Enceladus offers the fully assembled recipe for life. Looking back at the surface, those plumes shooting into the vacuum of space are more than just a geological curiosity. Other promising ocean worlds, like Jupiter's massive moon Europa, closely guard their subsurface water beneath miles of thick, impenetrable ice. Enceladus actively dredges up its deepest protected ocean contents and ejects them directly into orbit. This significantly changes the requirements for exploration. We don't have to build a nuclear-powered drill to reach the water. We just need a spacecraft capable of catching the spray as it passes. Today, Enceladus stands as the only habitable environment in the entire solar system, offering humanity pristine biological samples for free. Future space missions are now being designed to exploit this unique mechanism, building spacecraft to take advantage of these free samples drifting into the vacuum. Slated for the 2050s, the Enceladus Orbolander is a proposed flagship mission designed specifically to answer the question of life on this moon. The mission features a dual architecture. It will spend 18 months orbiting through the plumes to collect fresh material, before physically touching down on the South Pole for a 2-year surface study. Once there, its instruments will hunt for specific markers, amino acid distributions, complex cellular structures, and DNA sequences. The liquid water is there, the energy is there, the chemical building blocks are there. The ocean of Enceladus is fully prepped for life, and in a few decades, we are finally going back to see if anyone is home. Sitting nearly 2 billion miles from Earth is a pale blue dot with a bizarre characteristic. Uranus orbits the Sun rolling completely on its side, tilted at a 98-degree angle to the solar plane. Because of this severe orientation, the planet experiences punishing seasons. A single pole faces the Sun for 42 Earth years of pure continuous daylight, followed by 42 years of total darkness. William Herschel discovered the ice giant in 1781, but its immense distance meant it remained a blurry mystery to astronomers for over 2 centuries. To figure out how a sideways planetary system actually functions, humanity desperately needed a close-up look. That look finally came in January 1986, when NASA's Voyager 2 spacecraft made our first and only close encounter with the ice giant. Because the planet was pointing its pole directly at the Sun, Voyager 2 faced a grueling logistical constraint. It flew a bullseye trajectory, piercing the system in a matter of hours rather than the days it spent flying past Jupiter and Saturn. In that brief window, the probe returned a shocking discovery. Uranus possessed a highly erratic and asymmetrical magnetosphere. This diagram illustrates the magnetic field's geometry. Tilted 59 degrees and offset by a third of the planet's radius, it wobbles violently as Uranus spins. Furthermore, instruments detected an intense radiation environment devoid of plasma. Scientists concluded the system was totally sterile. For 38 years, this frantic snapshot became scientific gospel, defining Uranus as the extreme, dead magnetosphere of the solar system. But our foundational understanding of this entire planetary system was based on a massive cosmic coincidence. In 2024, researchers conducted a breakthrough reanalysis of the aging Voyager 2 dataset. They discovered that the spacecraft happened to arrive during an intense, highly anomalous solar wind event. This fluid dynamics model shows a massive wave of solar wind crushing the Uranian magnetosphere, squeezing internal plasma out the magnetic tail, a rare 5% event. Days earlier, Voyager would have seen its normal state, a relaxed magnetic field filled with dense plasma clouds. The conclusion that Uranus was a dead world was a temporary illusion caused by extreme space weather. The system is actually highly active. Normally, a planet's magnetic field traps the ions and particles released by active moons, creating a detectable signature of their internal activity. But because the solar wind had stripped the magnetosphere bare, the 1986 probe was effectively blinded to the geological processes occurring on Uranus's 29 satellites. We now recognize that the classical major moons, Miranda, Ariel, Titania, and Oberon, are not frozen remnants, but complex geological engines. Modeling now suggests that 4 of these moons likely harbor deep, shifting liquid water oceans, trapped beneath their scarred icy crusts. In fact, specific radiation anomalies around Ariel and Miranda suggest these moons may be actively venting subsurface material directly into space today. The planet itself is losing mass. Giant magnetic bubbles called plasmoids have been caught in the act of siphoning the Uranian atmosphere out into the void. Far from being a static, frozen tomb, the Uranian system is a dynamic environment that is actively shedding its atmosphere while hiding liquid water in the dark. Zooming out from our local solar system, astronomers have realized that ice giants are actually the most common type of planet found in the broader universe. Because they are the cosmic standard, decoding Uranus's bizarre internal water-ammonia mantle is essential for understanding the atmospheres of thousands of distant exoplanets. This urgency is reflected in the planetary science community's recent decadal survey, the roadmap that guides future space exploration funding. The survey officially designated a dedicated mission to Uranus as the highest priority flagship mission for the next generation of spaceflight. We cannot accurately interpret the galaxy's most common planets until we correct the 38-year misunderstanding of our own local ice giant. To solve this, scientists proposed the Uranus Orbiter and Probe, or UOP. It is designed to be a long-term presence in the system, rather than a fleeting flyby. The mission includes a sacrificial atmospheric probe that will ram directly through the negative 224-degree upper cloud layers, sampling the chemical makeup directly before the pressure crushes it. We already know the atmosphere is active. Recent infrared images from the James Webb Space Telescope have revealed rapidly changing dynamic cloud features that the aging 1986 data missed entirely. Resolving the boundary between Uranus's 13 chaotic rings and its shepherd moons demands years of high-fidelity observation from a stable orbit. To truly comprehend the hidden mechanics of the universe, humanity has unfinished business. We have to go back and properly meet the sideways planet. At the edge of the solar system, nearly 3 billion miles from the Sun, the incoming light is 900 times weaker than it is on Earth. By the 1840s, astronomers tracking the planet Uranus noticed that its orbit was drifting, pulled slightly off course by a gravitational force further out in the darkness. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently set out to find this missing mass. Using Newton's laws of gravity, they calculated the exact coordinates a hypothetical planet would need to occupy to cause the observed drag on Uranus. In September 1846, Le Verrier sent his coordinate calculations to the Berlin Observatory. On their first night of searching, astronomers found the new planet less than a single degree from where the math predicted. Neptune was the first planet discovered through calculation rather than visual observation, proving that the laws of physics could map bodies in the dark that human eyes had never seen. When NASA's Voyager 2 probe approached the distant ice giant in 1989, researchers expected a quiet, dormant sphere suspended in the deep freeze of the outer solar system. From a distance, the planet appears serene. Trace amounts of atmospheric methane absorb red light from the sun, reflecting a vibrant blue hue. Voyager's instruments revealed that this quiet exterior hides an atmosphere in total chaos. The upper cloud decks are shredded by retrograde winds blowing opposite to the planet's rotation. These gusts reach 1,300 miles per hour, 9 times stronger than the most severe hurricanes on Earth. This intense atmospheric shear generates massive anticyclones. Voyager captured a gaping hole in the methane deck called the Great Dark Spot, a storm system large enough to contain the Earth. Maintaining this kinetic energy requires a massive power source. While planets like Earth rely on solar radiation, Neptune drives the fastest winds in the solar system from a region of near-total solar deprivation. Tracking that power source requires descending thousands of miles beneath the visible cloud tops. Voyager's data shows a magnetic field that ignores the planet's rotational poles, tilted aggressively at a 47-degree angle. This field is also physically offset, originating from a point roughly 8,500 miles away from the planet's center. Terrestrial planets like Earth generate centered magnetic fields through solid, spinning cores. Neptune's irregular magnetic geometry suggests it lacks a traditional, centralized metallic center. Instead, the magnetic field points to a deep ocean of superpressurized, electrically conductive fluid in constant, violent motion. Sinking 10,000 kilometers below the clouds, The weight of the atmosphere above causes temperatures to soar to thousands of degrees. At this depth, the environment transitions into a dense mantle of superpressurized water, ammonia, and methane. Methane is built of one carbon atom bound to 4 hydrogen atoms. Under crushing mantle pressure, these bonds fail, isolating the carbon. Laser experiments replicate these conditions, proving that when compressed together, they form solid nanodiamonds. Inside Neptune, millions of carats of these dense diamonds slowly precipitate out of the hydrocarbon slush and sink toward the planet's rocky core. As this volume of diamond rain falls through the dense fluid, friction converts gravitational potential energy into intense heat. The planet is essentially a self-heating engine. This thermal energy boils upward from the core back toward the surface. The rising heat stirs the thick mantle of water and ammonia, powering the dynamo effect that creates the off-center magnetic field. As this heat hits the upper atmosphere, it drives 1,300-mile-per-hour winds and punches great dark spots through the cloud deck, revealing the turbulent layers below. Neptune operates as a self-sustaining thermodynamic system, decoupled from the energy of the Sun. Putting these internal physics into a galactic context reveals the significance of the ice giant. Astronomers surveying distant stars have discovered that Neptune-sized worlds are the most common type of exoplanet in the galaxy. The physics of diamond rain and internally driven winds define the standard behavior for thousands of alien planetary systems. Our data on this class of planet comes from a single brief spacecraft flyby in 1989. To map the mechanics of the galaxy's most common worlds, we have to return to the edge of our own system. Decoding the physics beneath that blue outer veil reveals the architecture of the most dominant class of planets in the cosmos. In August 2006, the International Astronomical Union gathered in Prague with an objective that would change our maps of the solar system. They were there to decide Pluto's fate. Following a period of intense debate, astronomers on stage raised their yellow ballots to officially redefine what it meant to be a planet. The assembly established 3 fundamental criteria. A planetary body must orbit the Sun, have enough mass to achieve a nearly spherical shape, and it must have cleared the neighborhood around its orbit. Because it shares its path with thousands of icy objects in the Kuiper Belt, Pluto failed that final test. It was officially reclassified as a dwarf planet, a status that invited the scientific world to dismiss it as a frozen, inactive relic. This demotion cemented a scientific paradigm that stripped Pluto of its planetary prestige, leaving humanity to view the world as a cold, dead ice ball. While that debate concluded on Earth, NASA's New Horizons probe was executing a 9-year, 3-billion-mile journey to the outer edge of the solar system. In July 2015, as the probe finally approached its target, ground controllers woke its instruments from a long cycle of electronic hibernation. The probe was so isolated that every packet of data it collected required a 4.5-hour transit to reach Earth, even traveling at the speed of light. When those initial transmissions finally rendered on our screens, the incoming data was on a direct collision course with a decade of entrenched scientific assumptions. The first major observation was a massive heart-shaped feature spanning the surface, known as Tombaugh Regio. The smooth left lobe of this heart, Sputnik Planitia, immediately stood out to geologists. It is a vast basin of nitrogen ice completely devoid of impact craters. In a region of space filled with ancient, battered terrain, a craterless surface means the ice here is remarkably young, less than 10 million years old. This cross-section shows how the surface is maintained. Internal heat warms deep nitrogen ice layers, causing them to rise from the bottom of polygonal cells. Reaching the surface, the warm ice spreads laterally, cools, and sinks back down along the edges. The result is a landscape of soft glaciers. The nitrogen ice constantly churns and flows, acting like a planetary slow-motion lava lamp. The active churning within Sputnik Planitia reveals a geologically living body, constantly erasing its own history and reshaping its own surface. Moving south from the glaciers, the terrain rises into 2 towering mountains, Wright Mons and Pickard Mons. They stand up to 7 kilometers high, each featuring a massive central depression or caldera at the summit. These structures are evidence of cryovolcanism. Instead of erupting molten rock like terrestrial volcanoes, they operate entirely on ice and freezing liquids. This diagram illustrates the mechanics. A thick slurry of water ice, methane, and ammonia is pushed upward through a central vent. The ammonia acts as a chemical antifreeze, maintaining a toothpaste-like consistency that allows the fluid to flow despite freezing surface temperatures. Discovering massive, recently active volcanoes made of ice indicates a robust and sustained internal heat engine. Prior to these observations, generating that much energy on a body this small and distant was considered mathematically impossible. The source of that unexpected energy lies deep underground. Inside Pluto's massive rocky core, the steady decay of radioactive isotopes provides a continuous supply of heat. This cross-section reveals how heat is conserved. An insulating layer of methane clothrate at the base of the crust traps thermal energy, preserving a global liquid water ocean up to 180 kilometers thick. This ocean explains a massive anomaly. Heavy nitrogen ice accumulated in Sputnik Planitia, pressing the crust and causing the ocean beneath to bulge. Tidal forces acted on this localized weight, forcing the dwarf planet to roll on its axis, shifting the basin's position. Today, enormous tectonic cracks stretch across the icy crust. Because water expands as it freezes, these extensive fissures prove the subsurface ocean is currently in a state of slow freezing and expansion. The existence of this liquid subsurface ocean elevates Pluto to the status of a complex world, capable of sustaining internal aquatic environments that were once thought impossible at this distance from the Sun. Returning to the 2006 IAU debate, the requirement to clear an orbital neighborhood seems increasingly detached from the physical reality on the ground. Pluto's geological complexity suggests that its status should be determined by what it is, not where it orbits. Many scientists, including New Horizons principal investigator Alan Stern, argue for a geophysical planetary definition. Under this standard, a planet is defined by its own internal properties, specifically having enough mass to pull itself into a round shape. This discovery places Pluto alongside worlds like Europa and Enceladus in the search for habitable environments, transforming our understanding of the solar system's potential for life. A moment of wonder. A final testament to its activity is visible at the very edge of space. A thin, glowing blue atmospheric haze surrounds the surface, actively replenished by sublimating ice from the glaciers below. Regardless of whether it is officially labeled a planet, a dwarf planet, or a Kuiper Belt object, Pluto redefines our understanding of what a living world can be, expanding our imagination of where life-sustaining oceans might hide in the dark. Look at this early diagram of the solar system. The concentric rings map planetary orbits, ending abruptly at Neptune, but observe the path of Halley's comet cutting across those tidy circles. Long-period comets dive into the inner solar system from unpredictable random angles. As they approach the Sun, they develop glowing dust and ion tails. These tails are evidence of active vaporization. Comets are fragile blocks of ice, literally boiling away in the solar heat. If these icy bodies permanently resided anywhere near the Sun, they would have vaporized billions of years ago. Yet fresh comets continuously arrive in our sky. Where is the supply coming from? To account for these inbound objects, the physical boundary of our solar system has to be vastly larger than the map of the planet suggests. In 1950, Dutch astronomer Jan Oort proposed a solution to this missing source of comets. He deduced that there must be a massive hidden reservoir of ice far beyond the planetary orbits, acting as a deep freeze that occasionally drops material inward. Oort built this theoretical framework mathematically, expanding on earlier calculations by Estonian astronomer Ernst Öpik. To find this reservoir, we have to leave the visible planets behind and travel outward into deep space. Mapping the true edge of the Sun's domain means stepping into a region where we cannot rely on observable light, but rather on gravitational deduction. At these distances, miles become useless. We measure the journey in astronomical units, or AU, where 1 AU is the distance between the Earth and the Sun. Moving outward, we pass Neptune at 30 AU and clear the icy debris of the Kuiper Belt by roughly 50 AU. It isn't until roughly 2000 AU that we hit the inner Oort Cloud. Rewinding 4.6 billion years shows this material's origin. Pristine icy planetesimals clustered near forming gas giants. As Jupiter and Neptune grew, their gravity kicked these bodies outward, rapidly scattering them into space. The inner Oort Cloud now acts as a cosmic graveyard, storing the exiled planetary building blocks from the solar system's turbulent youth. Pushing further out, we enter the outer Oort Cloud. This region spans from 20,000 AU to well over 100,000 AU, stretching up to 3.2 light-years from the Sun. Here, the flat inner disk expands into a massive, sparsely populated spherical bubble. A gravity heat map shows why. At extreme distances, the Sun's grip fades to near zero. Instead, the Milky Way's galactic tide exerts a steady torque, circularizing the orbits into a three-dimensional sphere. The architecture of the outer Oort Cloud is maintained by a delicate gravitational tug-of-war between our Sun and the rest of the galaxy. Because these comets are so weakly bound to the Sun, their orbits are incredibly fragile. External forces, like a passing star or a massive, dense molecular cloud, can easily disrupt this delicate balance. In 1.3 million years, the star Gliese 710 will pass close enough to gravitationally drag icy chunks right out of their dormant positions. Once an icy body is knocked loose, it begins a slow, million-year freefall back toward the Sun. Every newly discovered long-period comet in our sky is the direct result of a random galactic encounter millions of years in the past. Mathematically, this theoretical structure contains trillions of icy bodies, with a total mass of up to 5 Earths. Yet despite its immense size, the Oort Cloud remains entirely unobserved. The objects are simply too dark, sparse, and distant for any modern telescope to capture. To ground that distance, consider Voyager 1. It is the fastest, farthest spacecraft humanity has ever launched, but it will take another 300 years just to reach the cloud's inner edge. Its power supplies will have been dead for centuries before it ever crosses that threshold. The Oort Cloud remains a theoretical certainty, a region we know mathematically must exist, even if we cannot directly witness it. This is the absolute edge of the solar system. It is the specific perimeter where the Sun's gravity finally surrenders completely to interstellar space. The comets that fall from this outer darkness are pristine time capsules, carrying the untouched chemical building blocks of our planetary genesis. A passing comet serves as a visible bridge, linking the deep past of planetary formation to the absolute limits of our cosmic neighborhood.